campaigns and leads business development to explore innovation opportunities for additional applications for EV charging, as well as applications for inverters. After this presentation, we're going to have a live Q&A session with Nick. So you can submit your questions at any time. If you at the Q&A, the Q&A chat box that you see on the right-hand side of your screen. So thank you everyone for joining, and with that, we'll hand over to Nick for the presentation.
Hi everyone. Yes, I wanted to discuss the role of power conversion in EV charging innovation. And for our agenda today, we're going to cover power modules and level 3 or DC fast charging applications, power conversion in general and input agnostic modules, and then cover a bit of Q&A. And first, we'll go ahead and cover how power modules fit into level 3 or DC fast charging applications. But before I wanted to go ahead and just jump into DC fast charging, I wanted to provide an EV charger overview. So you've just heard me mention level 3, but I want to go ahead and build up to what does that mean? So for level 1 EV charging, that's generally what you'll find in the trunk of your car when you buy an electric vehicle. So again, generally speaking, these will plug into 120 volt AC circuits, be around 10 to 15 and sometimes 20 amp circuits. So again, anything that you're going to find in your normal wall outlet or so forth. But there's also what's called level 2 charging. And these will be 240 volt single phase circuits. Sometimes they will be 208 volt circuits, depending on what your application is. But typically they're going to be 240 volt single phase circuits. And for a home charger, they're going to be 32 amp, but they can be 40 amp, 48 amp, and 80 amp circuits in the US. Again, all those being 240 volt AC single phase circuits. And what you're going to see here is a couple different ways that those level 1 and level 2 circuits are going to plug in. They're going to plug into what's called an onboard charger. So all batteries are DC, whether it be 400, 650 volt, 800 volt circuits. But at the end of the day, they're all going to be DC. So the responsibility of this onboard charger is to take that AC voltage that you're getting from the utility, from your wall, etc., and convert that to the appropriate voltage of the battery. And again, this is what we most commonly do at home, sometimes out in public charging and so forth. But for large fleets where you don't have the amount of time to charge, because as you can see here, for some of the power levels, sometimes less than 4 kilowatts. All AC chargers in the US are going to be less than 20 kilowatt. When you're talking about 60, 80, 150 types of kilowatt hour batteries, that can take an immense amount of time to charge. And you may not have that time to charge. So a product line built around level 3 or DC fast charging is bypassing the onboard charger on board and going directly in the vehicle. And that's what you see in that green square in the slide here. So what that's doing is taking all the power conversion that's within the onboard charger, which the onboard charger can still be there, that's taking that, and the charger is communicating to the vehicle to match the voltage, basically doing all the behavior of the onboard charger and building that into the charging station itself. And so that's matching the vehicle battery voltage, whether it be 400 or 800 volt, 650 volt, whatever it may be. and just directly charging the battery on the vehicle. And so there's many different ways to do that in terms of connectors, and you're going to see a number of them that are listed here on the screen. But in the US, what's typical today is a CCS1 cable. So it's going to match the J1772 footprint when you plug it into the vehicle, but it's going to have two DC pins at the very bottom. And that is what's actually delivering power to the battery. So again, matching the same AC ports here, but power actually delivered at the bottom. Now, in different countries, different regions around the world, there's a lot of different ways to do this. What's coming in the US is what's called NACS. And this is typically referred to as the Tesla charger and so forth, and something that is coming, but not here quite yet. Future 2026 model years are going to have these connectors on board. But basically, it's taking those 240 volt AC single phase pins and turning those into DC pins. And depending on how your vehicle communicates, it's going to recognize, hey, this is what charger I am. I'm going to be going in, I'm an AC charger. I'm going to go through your onboard vehicle or onboard charger on the vehicle. Or it's going to say, hey, I'm a DC charger. I'm going to deliver power directly to your battery. So that's what's coming here actually very shortly. But generally speaking, what's here today in the US is a CCS1. So I mentioned taking the onboard charger and implementing that into DC fast charger. So an onboard charger, again, what it does is it takes the AC voltage and converts that to the appropriate DC voltage for the battery. Now, what a DC fast charger does is it does that in a set of rectifiers within the DC fast charger. And generally speaking, because you're trying to charge at faster speeds, again, AC chargers are limited at 80 amps input at 240 single phase. You're at 19.2 kilowatt. You want a DC fast charge, you want to charge faster. So the rectifiers that are in DC fast chargers are wanting to charge faster, so there's going to be a lot more power inside the DC fast charger. And in most cases, this is going to be from 30 kilowatt, 60 kilowatt, 120, and sometimes they can reach up to 480 kilowatts. And with that, based on the amount of power that you have, that's going to dictate the size of your charger and so forth, the power output, and there's a lot of other things that are needed to be considered when looking at a DC fast charger. And they can be uptime and reliability. When you look at a DC fast charger, one of the main components is of course the rectifier, and a rectifier takes AC to DC to match those battery voltages. So uptime, reliability, the ease of maintenance and access inside the charger, as well as the overall compatibility of the charger with the voltage configurations and topologies that are available in the US. All of these are going to be very critical in terms of selecting a DC fast charger and applying it into your overall charging scheme. So Lydon has made a number of different server and data center rectifiers to take that same AC voltage and provide, whether it be 12, 24, 48, 51 volts, whatever it may be, but basically constant voltage types of rectifiers. And PAI Power Innovations International, being a division of Lydon, has taken that same type of power supply topology and modified that to be an EV charger rectifier. So what this means is that the typical battery voltages that you're going to see in a passenger vehicle are going to be, again, 400, 800 volt. Commercial vehicles, oftentimes 650 volt. But we have taken that same type of topology and adapted it to the wide range outputs that you're going to find in the field. You never know when you're going to plug into a 400 volt vehicle, 800 volt vehicle, 650 volt vehicle, whatever it may be. So having a wide range output on the rectifier is critical to DC fast charging products. So for PII, we have a 250 to 920 volt output to our products. And because these are outdoor installations and not data center, having a wide operational environment is also critical to maintain the uptime and reliability requirements that the industry has. Now, there is a kind of a stigma, I guess, with DC fast charging in general, where a number of different stations would be down, but we have taken this same type of topology that is proven in the server and data center rectifier space and applied that to DC fast chargers. Now, we've done that in an enclosure that makes sure that we maintain a very reliable environment, but that's something that we have done for the DC fast charging space. So I want to talk a little bit more about power conversion and how we take these power supplies and create an input agnostic environment with our power conversion modules. But before I do that, I want to cover a little bit about who Power Innovations is. So Power Innovations was founded in 1997 around a UPS product line that's for mission critical applications. So we talk mission critical applications. We're talking about flight simulators. You go into any airport around the United States, you're going to see the X-ray equipment and so forth. And what backs that up in terms of power is a Power Innovations UPS. So very quality power going to these mission critical systems, and it extends out beyond that. There's applications for offshore oil rigs, or there's public transport, all applications that PII has supported over the years. And in 2013, Power Innovations was acquired by Lyton, but maintained the core competency of integrating power conversion into overall assemblies in mission critical applications. So PII is based in American Fork, Utah. It's right outside of Salt Lake City. And across that time, there's been a number of other different low voltage power distribution that has supported the UPS product line. And in 2021, 2022 timeframe-ish, PII looked for areas that are complementary to what Lydon does. Lydon is the #1 manufacturer in volume of level 2 EV chargers. What PII does is integrate power conversion for mission critical applications, and thought that this adjacency for EV charging in terms of what Power Innovations does and power conversion integration, what LEDON knows already in electric vehicle charging infrastructure, and created a line of DC fast chargers, leveraging a lot of the things that PAI and LEDON already knows today. So I walked through a little bit of the history of PAI, but again, at the end of the day, starting in UPS, growing into different types of systems. Again, LEDON acquired PAI in 2013, and have gone through an expansion of the portfolio here recently to develop a line of 30 up to 180 kilowatt DC fast chargers. So at the heart of a DC fast charger, again, is the rectifier itself. So what you see here is a flexible input source rectifier where the input would be 90 to 315 volts AC, or we have a 200 to about 440 volt DC input option. Now I say an option, but it's really all in the same rectifier. And this allows the rectifier to be used in a number of different use cases, whether it be typical grid voltages or with a DC input, perhaps from a battery source, perhaps from a fuel cell source, and the latter two being ones that you can essentially ensure that it's a green renewable energy source. These are a 3.3 kilowatt rectifier. We arrange these in a shelf to be 10 kilowatts, which I'll cover here in a minute. But these provide the wide range output, 250 to 920 volts DC, for certainly charging electric vehicles, but other battery packs, and just generally speaking, providing the source to provide power to other DC loads. Each one of these is galvanically isolated from the input and the chassis, and can provide constant power and constant current, particularly that are needed in EV charging applications. PII does is we take these 3.3 kilowatt rectifiers, and what you see on in this particular slide here is what we call an EV charging power pack. So each one of those rectifiers that you saw on the previous slide are again arranged in a 10 kilowatt shelf, 3.3 times 3, totaling up to 10 kilowatt. And on the again upper left, you see 6 shelves, that totaling to be 60 kilowatts of power conversion. Now on the top section, there's what we call a rack controller, and that rack controller provides many different functions within the overall system. So that provides input power measurement, that provides a little bit of offtake to provide any of the other low voltage loads. So you're going to need 12 volt loads, 24 volt loads, as well as sometimes 48 volt, which we do for our thermal management. And it then sends that power to each one of the rectifiers. The rectifiers perform their power conversion and combine that power into a common DC rail in the middle. All of those communicating to each other to sync up and provide the same output voltage that the vehicle needs as it's delivering power to the vehicle. So power comes back through the rack controller and out if you look at the picture on the upper right, out a terminal block where our CCS1 or NACS cable would exit, and we simply provide that power out, back out to the vehicle. Now, with this arrangement of 3 rectifiers within a shelf, what we do is we have 3 pairs of voltage inputs to each one of the rectifiers. So we're capable of taking 240 single phase, 3-phase delta, in our case, that would be 208 or 240 delta, or 480 3-phase Y as an input to this EV charging power pack. And the pictures here may not be in size proportion with each other, but basically this bus bar that you see on the lower left fits about in the palm of your hand. And it's very simply configurable. So each charger that we provide is provided with each of the bus bars. And again, very simply, at a maximum of 10 socket head cap screws, would be able to insert one of the bus bars to the corresponding input voltage and be able to provide EV charging to the vehicle that you're attempting to charge. Very simple. Again, 3 bus bars that fit in the palm of your hand and very simply integrated into the overall scheme that you see on the bottom right. So again, just a little bit more about the EV charging power pack. So with this power pack, it mounts within a 19-inch EIA rack. Again, each of the shelves contains 10 kilowatts of power. This shelf, being that it fits into a EIA 19-inch rack, uses a lot of the same overall core competencies of Lite-On overall. And we use a lot of the same measurements. So this fits into a 1U shelf or 1.75-inch shelf. Whereas again, the top rack controller controls the bottom downstream shelves. And again, in this case being 6 shelves. So overall, you have a total height of about 8.5 U or about 15 inches tall. And all of the input voltages that you see here, 240 single phase, 208 or 240 3-wire systems, 480 Y 4-wire, or a 200 to about 450 volt DC input are all acceptable inputs to this EV charging power pack. Now, while we do that, we're able to provide an output voltage from 250 to 920 volts DC. And one thing I did not describe about what this power pack does is that it, does the power measurement, does the offtake of doing auxiliary power, but it also includes the power line communication or PLC communication via the top printed circuit board to communicate to the vehicle to do DC fast charging. Again, DC fast charging, we have to match a number of different things. One of them being the voltage that the vehicle requires, plus a number of other different things. But we can include all of that capability within the rack controller contained within our power pack. So when we create the power pack, whether it be a 60 kilowatt, which we've spoken about, but also we can as we're very modular in the power overall power topology within our product line, we're able to take that same overall architecture and create a 30 kilowatt, 60 kilowatt, 120 kilowatt system by using the same core power modules. So our overall product line, whether it be a quick charger, which we consider a 30 and 60 kilowatt, or a fast charger being 120 up to 180 kilowatt, all benefit from the same modular solution that, again, spans many market needs, whether it be from a fleet solution all the way to public charging. And this helps increase the installation time as we're using the same core building blocks, allows greater application flexibility, and overall reduces the inventory costs when we're talking about power modules. So I'm going to spend a little bit of time talking about PII's unidirectional DC fast charging product line. So our product line extends from a 30 kilowatt pedestal. I say pedestal, but it also is a wall mount unit, with the pedestal or wall mount unit sold separately. The same base and core charger itself can be implemented into a wall mount or a pedestal unit. We have a 60 kilowatt pedestal unit, and we have what we call mobile charging units. So we have an indoor mobile charging unit as well as an outdoor charging unit. So depending on what the application needs are, in an indoor unit, we are again shrinking down the size a bit, where we don't need necessarily a sealed unit being indoors. We can use the ambient air to help provide some of the cooling. In an outdoor application, and this extends for all of the outdoor products, we leverage a air-to-air heat exchanger, where we essentially have a sealed unit where we're not having filters or anything bringing outside air, blowing across a filter, blowing across your electronics. So any of our outdoor product line, we have a sealed unit where we have an air-to-air heat exchanger, and that's what our outdoor mobile features, as well as our 30, 60, and 120 kilowatt stations. And then we finish up with the 120 to 180 kilowatt station. This is being an all-in-one unit. The power conversion, the dispensing is all in one unit within this particular charger. So we talk about a little bit about more of the features that we have within the PII product line. So as you saw, we have a 3.3 kilowatt module. These are actually field replaceable modules. So and with an LED on the front that can tell you status, of course, we can also monitor those modules and their behavior in the field. Now, we don't expect an issue, as we have, as I mentioned, we're leveraging the same power conversion topology as what exists in the data center today. So that's a demonstrated greater than 1 million hour MTBF on that power supply topology. But you would be able to continue monitoring what is occurring in those modules in the field. And if there are any issues, we do have field replaceable modules. So I mentioned that you can take a number of different input voltages, 240 single phase all the way up to 480 three-phase Y, and we're able to accept those input voltages with no derating. So there may be another number of different manufacturers that can do different input voltages, but you may lose some of the power that you actually purchased. We're able to do that, accept all those voltages, but not lose any of the power that you purchased. Some of the other ones you may be familiar with. So any of the upgrades or adaptations that need to occur in the field. So for instance, if you have a new vehicle that comes out that's maybe a little bit different, communicates a little bit differently than what may have existed in the previous model year, we're able to provide those updates to communicate to that vehicle in the field. One thing that is certainly a hot topic is bidirectional charging. And what's typically existed in the past is maybe two ways of doing bidirectional charging. One is through say offloading or maybe charging the vehicle via AC and then offloading power via DC. Or that was of course the Nissan Leaf, which uses a CHAdeMO structure, which is a little bit different in the US and widely adopted. And so PII has a couple of unique solutions to support bidirectional charging but still maintaining DC to and from the vehicle. And in starting, we don't have to change our core topology, our core architecture of our product. So what you see on the top left is our unidirectional charger architecture, where we have a charge controller, or what I was mentioning as a rack controller, and having different rectifiers that get distributed power, but then reaccumulate power in the rear to provide power to the vehicle. And what you see on the far right here is our approach to bidirectional charging. So PII has an inverter, which I'll cover here in a minute, where we can create a paralleled powertrain maintaining our rectifier topology, adding in the inverter in parallel to where we can charge and discharge vehicles through a similar type of architecture. Now, there's some other things that are covered on the slide here, but I want to make one point clear is that what's shown here is 3 shelves. That's not only 3 shelves. It's just a simplistic view of showing rectifiers and inverters, but the power levels are, again, very modular. You can stack on 30, 40, 50, 60, whatever it may be, onto a singular power pack to create that bidirectional power flow. Really one of the things that we're trying to articulate here is that we're very scalable to meet a number of different applications, EV charging, of course, being one, but EV discharging also being another. So our hybrid inverter, and I'll touch on what hybrid inverter means here in a minute, but this particular product here is a 400 volt nominal DC input, 250 to about 440 volts DC input. And again, as you see, it's the same footprint as what you saw of the rectifier. It's a 3.3 kVA output, where hybrid, again, can mean two things. So in a vehicle to grid application, particularly for home environments, you're typically going to need a 240 volt single phase. This inverter here is a 120, 240 volt split phase inverter. So it can provide vehicle to home backup power. It's also grid forming as well as grid following. So when we talk about V to H being grid forming, V to G being grid following, it can do both of those modes. But again, also providing split phase power. Don't need to use the neutral. Can provide again 120 using the neutral, as well as 240 for V to G. Now, if you're using 480 applications, again, stringing those three into the three modules into a shelf, it also can provide 277 volt output to provide a three-phase output that matches the 480 volt Y of the rectifier. Just one view of what we call an inverter pack. We've used this on hydrogen fuel cell applications as well as battery applications. But in this case, what I wanted to show here is that we use the same system controller or rack controller to provide any of the monitoring and control of the downstream inverters in this case. And what's shown here is a grid forming application. So this is a generator application where we're showing three shelves of inverters that each and of themselves form a phase of three-phase. So three shelves, three phases. I mentioned providing 120, which can create 208 volt Y. We also have 240 delta, 415 Y, 480 Y outputs that can be formed from these shelves. And in the bottom shelf, again, it's just more of a demonstration, which we've also done, is where we can provide single phase output, 120, 240, 277, but as well as 120, 240 split phase outputs. So again, these mount in a 1U shelf, 10 kVA per 1U shelf, adding on a system or rack controller at the top to control each one of the downstream inverters, creating the discharging within a bidirectional charger. So I mentioned a parallel powertrain. So this is, again, a very simplistic view of providing power to and from the grid over to an electric vehicle, in this case, a school bus. So we have 10 kilowatts per shelf of rectifiers, 10 kilowatt or 10 kVA of inverters per shelf. And again, in this particular case, arranging those rectifiers to provide, in this view, 30 kilowatts of charging to the vehicle and 30 kVA of discharging from the vehicle back to the grid. And because the rectifiers themselves are very highly input agnostic, taking 208 up to 480 three-phase, the inverters do likewise. So it can power match for whatever overall power distribution topology is required of the application. That's not to say that you need equal charging and discharging. So with PII's bidirectional charging system, you're able to charge and discharge at different rates. So in a 60 kilowatt power pack, you're able to charge, for example, at 20 kilowatts and discharge at 40 kilowatts, or charge at 50 kilowatts and discharge at 10 kilowatts. It really doesn't matter the overall structure. It's simply stacking rectifiers and inverters to meet any of the different input voltages that you would have, or the grid voltages that you would have in your particular application. And again, they can be configured to any input voltage. It does not require equal power to and from said vehicle to accommodate the different voltages that I've mentioned here. So for PAI's bidirectional charger product line, what we are doing is leveraging our existing unidirectional charger structure to create that bidirectional product line. So I mentioned our 30, 60, all the way up to 180 kilowatt systems, and we're able to leverage that same overall mechanical structure of what houses the power packs and take that same structure and leverage it to bidirectional. So for a 60 kilowatt unidirectional charger, for example, you may get 30 kilowatt bidirectional capability out of that. And again, it doesn't matter necessarily of making sure that you have equal power. It can be 20, 40, 50, 10, whatever it may be. But all of that is capable of within the 60 kilowatt unidirectional pedestal. So you can think about it as I have 60 kilowatts of total power. It's up to me to divide that and allocate between charging and discharging. And the same thing for our 120 kilowatt unidirectional station. Yes, this is an all-in-one station. What you may be familiar with in the industry is a PCS cabinet as well as a dispenser. We do all of our bidirectional charging within the same overall cabinet. So your power conversion and vehicle communication and your dispensing is all done with one unit. So for 120 kilowatts of a unidirectional station, I can divide that to up to about 90 kilowatts one way or the other. So in that case being a 90-30, 80-40, whatever it may be. So now, at this point in time, I'll go ahead and open up to any questions.
Well, thank you, Nick, for that great presentation. I know I learned a lot about this important aspects of EV charging technology. I see we already have several good questions ready to go, but I want to remind the audience that there's still time to submit your questions in the Q&A tab. So with all that said, Nick, are you ready to answer some questions?
Yep, absolutely.
Great.